Hello all, my name is Sandeep Madisetty. I'm here to present the course project work for Machine Learning Foundations for Product Managers course from Coursera. So as part of this project, we are given a set of data with some data points, and the ask is to create a machine learning model that can accurately predict uh, the energy power generated uh, by evaluating the four parameters data points, which is ambient temperature, vacuum, ambient pressure, and relative humidity. So to begin with, I spent some time to understand how the combined cycle power plant works. I tried to understand how each of these variables, temperature, vacuum, pressure, and humidity, are related, and figured out that temperature and humidity are inversely proportional, and the pressure and vacuum, so forth. So I thought we can pick one or more of these related data points as the input features to predict the power generated. So I decided to pick the ambient temperature and the ambient pressure as the input variables to predict the power generated. Now, given the entire set of data, I split the data into two sets, training set and the test set, in the ratio of 80-20. 20% of the data is taken as a test set and 80% as a training set. And I further divided the training data set into two batches so that we can use the cross validation method. Uh, Training validation set 1 and set 2. So in the first I let's start with the training and validation set 1. So we have the input parameters temperature and pressure here to predict the outcome, that is power generated. Uh, since we decided to use the linear regression model, I use the Excel's inbuilt regression functionality on these two input parameters, and this being the output parameter. And you can see the results here. Uh, so we have the R square value as 0.8, which is close to 1, which indicates that it's a very good, the model is a very good fit, and it is able to predict the outcome variable using the input parameters or input features uh, with a greater accuracy. Uh, and you can see the intercept value here and the coefficients for the both the input features. Now, since we notice that this the model has yielded some good results here in terms of fitness, I applied the model outputs onto the training set to see to evaluate how the training model results look like. Uh, so here is the training operated on the validation batch 2 here. So you can see you have the input parameters here, the features, temperature and pressure, and the output parameter, and it is generated using the coefficients and the intercept from the training set 1 using the formula y is equal to mx plus c. Here are the prediction values uh, on the training set 2, which is used for validation. So we calculate the predicted value here in column H and the residual value in column I. Residual is nothing but the difference between the actual value and the predicted value. Now, using this data, calculated the standard error, and which is 5.3, which is close to what we got from the initial training set here, right? Yeah. Exhibiting that the variation in the error is very less, and also the MAPE value that is calculated from this data is 0.95, which is close to approximately 10%, less than 10%, which again indicates that this model is a very good fit, telling us that the difference between the the actual value in the predicted value is less than 10%. So it's a very good fit. Now the next step was to use the validation set 2 as a training data and apply the model results from the training set 2 on set 1 to check the results. So I ran the same regression model here on training set 2. Let me unhide them so that you can see here. And if you can see the model results here, the R square and the adjusted R square value are pretty much same what we got from training set 1, right? Which indicates that there's not a lot of variation in the output generated here, and the standard are also being the same, close to 5.3. Here we have the intercepts for both the input features, coefficients and the intercept. So using these values, I did the predictions. So basically using the results from the regression model run on training set 2, I used to test them the validation set 1. If I unhide this, you can see. So using the formula y is equal to mx plus c and the coefficients and the y-intercept from the training from set 2. These are the predicted values in column H, and I use the residual values. And again, if you look at the standard error from these calculations and the MAP value, they are pretty much same what we got from the initial training set. So there's not a lot of difference, indicating that there is not a lot of variation in the data, and the linear regression model is yielding almost the same results in both the cross validation sets. Now, having done that, we intend to apply the model results on our actual test set that is segregated initially, which is 20% of the original data. Let me unhide these columns. Right. So again, here we have to get the projected value based on the training model that we had. So what I did was took the intercept and the coefficients from each of the training set 1 and set 2, and got an average of them. I use this average value in using to derive the predicted value on our training data set, and here are the results in column H. Again, column I gives you the residual value and J the MAP values, calculation for MAP actually. So from this we calculate the standard error and the average MAP value. It is pretty much same what we got from the initial training and validation set. Standard error variation being 5, very less, and the MAP value very close to 1, which is 10%, and that indicates the model is a very good fit. So from all these observations, we can clearly conclude that ambient temperature and ambient pressure are the appropriate input features that we can use for this prediction model using a linear regression algorithm, which is giving the predictions very accurately with a very less scope for error and good performance. So we can conclude that this model is an appropriate fit. As asked in the assignment, I also tried to do the same predictions and model using the other two parameters that we did not consider in this iteration, which is your vacuum and the relative humidity. So I just again split the data into two sets, just a test set and a training set, and I took the vacuum and the relative humidity as the input features, and the energy generated as the output feature. I applied the uh, linear regression model, and you can see that the R square value is 0.7, adjusted R square is 0.7, standard error is 8. And if you compare these results with our initial uh, our initial model that we ran under different input features, uh, these are slightly those were slightly better than this, because the standard error in that model, if you see, was uh, close to 5, and the MAP was 0.94. But when we change the input features to vacuum and relative humidity, the standard error slightly increased to 8.2, which is approximately 3 units, and the MAP is 1.4, which is 14% differentiation. So I applied the coefficients and the intercept values on the test data to arrive the projected value. So basically, to testing the model on the test data, and here are the projected values on the test set. Column G, H is the residual, and here the calculations for standard error and MAP. Again, they are pretty much close to what we saw from the training set, 8.2, 1.4. Here also we got the same values. So we can fairly conclude that the input features that we selected in our first iteration, which is basically your temperature and pressure, are definitely yielding a better predictions in the linear regression model, and giving us a very good fit model as compared to uh, the other two input features that we took in the second iteration. So it is a fair conclusion that ambient temperature and pressure are the appropriate input features in the given situation to predict the energy output, and the linear regression model is also best fit in this situation, because we see clearly that the model is able to predict predict the output variable, which is energy generated, with very less error margin, and a very good MAP, which is our evaluation parameter. So this concludes the course project. Thank you for your time.